Hello, thank you so much for tuning into my presentation. Today I'm going to talk about the role that angiosperms may or may not have played in facilitating the taxonomic diversification of insects. I'll start with a brief comparison of the fossil records of insects and of plants. I will get into some of the ideas that underlie the current consensus of the role that plants played in shaping insect diversity. And then I will show new reconstructions of the taxonomic diversity of insects in deep time. And vascular plants originated during the Silurian. In contrast, winged insects did not originate until the Carboniferous. Almost all insects that are alive today have wings, or at least their ancestors have wings, and wings are one of the two key innovations that are credited with facilitating the tremendous diversity of insects. But you can see that there's a lag of many tens of millions of years between when vascular plants were on the landscape and available for insects to eat versus when we have winged insects. But then pretty much as soon as we have winged insects, we have whole metabolous insects. So these are insects that undergo complete metamorphosis, such as a maggot turning into a fly or caterpillar turning into a moth. Along with wings, holometabole is the second key innovation that has been credited with the evolutionary success of insects. And many divergences happened in the insect phylogeny between the origin of wings and the origin of holometabole. But as you can see here, these two innovations originated in very, very rapid succession from each other in a geologic sense. And then pretty much as soon as we have holometabole, we have stem beetles. We have insects that are more closely related to beetles than to anything else that's alive today. And as you probably know, beetles are the most diverse group of animals that we have today on this planet. So very quickly after winged insects originated, we had insects on the landscape that would have appeared fundamentally modern to a person from today who would have traveled back in time. And then in contrast, the plants that we think of as fundamentally modern, the angiosperms, appear not to have originated until the Cretaceous. And so we have this period of tens of millions of years in which insects were fundamentally modern in a way that plants were not. And so I think that this is a really fascinating time period in Earth history for paleontologists who are interested in questions of contingency. And so now I'm just going to briefly go over the role that many people believe that plants have played in the diversification of insects. And so this tends to focus on angiosperms. With angiosperms, we have very good reason to believe that their taxonomic diversity has increased steadily from the Cretaceous until today. And in addition to that, the spectacular hydraulic capacity of angiosperms compared to other plants means that once you have a landscape that's dominated by angiosperms, you can have a great increase in the total amount of plant biomass that is on that landscape. And so thinking from the perspective of an herbivorous insect, these insects have more diverse food to eat and they have more abundant food once angiosperms really do take over. And so the current consensus is that angiosperms facilitated the diversification of insects that we see the results of today. Unfortunately, this cannot be tested directly with the fossil record because insects don't have nearly as good of a fossil record as plants do. And in addition, there's a question of taxonomic scale, right? So if you were to go back to the point in Earth history when there were half as many orders of insects as there are today, that was way earlier on than the point in Earth history when there were half as many genera as there are today. So diversity at the level of order increased much earlier and much faster than diversity at the level of genus for insects. And of course, between the taxonomic levels of order and genus, you have the taxonomic level of family. And so then the question is, where do families fit in? Because families are the finest taxonomic level for which we do have enough data to reconstruct insect diversity in deep time. And so there are two techniques that have previously been used to reconstruct the taxonomic diversity of insects. The first and simpler of the two is the range-through method. So what you do is you assume that every insect family existed between its first occurrence and its last occurrence in the fossil record. One disadvantage of this is that it doesn't fully account for the incompleteness of the fossil record. Because the fossil record of insects is pretty spotty, we usually don't have good reason to believe that an extinct group of insects truly was absent from the landscape after its last occurrence that we know of in the fossil record. But one advantage of the range-through method is that families are not treated as missing from the middle of their ranges, even if they don't appear in every single interval in the middle of their ranges. And then the other technique that's been used is called shareholder quorum subsampling, which I'll just call SQS because it's a bit of a mouthful. And this is a more complicated technique. It is somewhat analogous to rarefaction, but essentially you subsample your data, you continue sampling your data until you have reached a standardized share of families from each interval. And the share that each family comprises is the proportion of occurrences in that interval that belong to that family. So one advantage of SQS is that it accounts for the fact that you have different numbers of families preserved in each interval due to the quality of the record. But one disadvantage is that if a family is missing from the middle of its range, SQS will reconstruct it as having been absent. And then another disadvantage is that whenever you're subsampling, you're throwing out some data. And so now I'm going to show the results of those two methods. So the first is range through, and you can see that we have essentially a steadily increasing amount of insect diversity at the family level through time. In contrast with shareholder quorum subsampling, we have an extremely volatile taxonomic history of insects, and this volatility is all the more striking when you keep in mind that this diversity curve is not showing genera, it's showing families. And so here we have the two diversity curves plotted together, and you can see that they are very, very, very different from each other. And it's impossible to reconcile these two reconstructions of taxonomic diversity of insects in deep time just using what we know from these methods. So today I'm going to show you new results that I got using the capture mark recapture or CMR technique. And so capture mark recapture was originally developed to track individuals within a population of wildlife, but we can also use the exact same arithmetic to track taxa in deep time. One thing that's great about CMR is that it has the advantages of both range through and SQS. So families are not missing from reconstructions generated with CMR in the middle of their temporal ranges, even if they are missing from some of those intervals. And we're not throwing away any of the data. But also, we are accounting for the fact that we have different numbers of families preserved in each interval due to the variable quality of the fossil record. And CMR also has a unique advantage, which is that it recognizes that families might not truly be extinct as soon as we are after their last appearance in the fossil record. And so what CMR does is for each interval, it calculates the proportion of missing taxa that must have existed and incorporates that into the arithmetic that's used to generate an estimate of total diversity. So this is what we get when we estimate insect diversity in deep time with CMR. You'll see that there's a few different curves. The solid one includes amber, and then the curve with the dashed line does not include amber. And then these different colors here represent different estimates of what the diversity of insects that we see today will look like in the future, because CMR does not reconstruct diversity up until the very last interval for which information is available. But nevertheless, there are some features that we see that are robust to any of these different sensitivity tests. The first is that diversity levels, again at the level of family, diversity is essentially the same between this point in the Cretaceous and this much more recent interval here. So this shows that at the level of family, insects were diverse in a modern sense going back into the later part of the Mesozoic. Something else to notice is that around the time that we have the first definitive angiosperms in the fossil record, we also do see a local peak in diversity right there. And then as angiosperms are diversifying on the landscape, we see this even higher peak in diversity. But we see insect diversity increasing even during intervals in which we don't have evidence of angiosperms, and intervals for which we can be confident that angiosperms would not have been dominant on the landscape even if they really did exist. And so that includes the beginning of the Cretaceous as well as the later Jurassic. This shows us that family level insect diversity during the early Cretaceous was approximately as high as it is today. And this cannot be attributed to angiosperms because it predates angiosperms. So the diversification of insects is happening before angiosperms evolved, and this diversification reached a peak tens of millions of years before angiosperms were truly dominant on the landscape. And so this raises the question, if angiosperms didn't cause this peak in insect diversity, then what did? And I believe that the answer lies in the ecologies of these insect families. So in this graph here, we have different orders of insects along the bottom that are arranged in a phylogenetic sequence. Each of these white bars represents the number of families in each order that went extinct during this Jurassic through Early Cretaceous interval in which we see this diversification of insects. And these bars that are filled in with different colors, such as blue and black, these represent the number of families in each order that originated during this interval. And so here in red, these are the insect families that are parasitic or parasitoid. The vast majority of these don't parasitize vertebrates like us, they actually parasitize other insects. And we can see that Hymenoptera, which is the order of insects that includes wasps, this is the order of insects in which we see the most dramatic diversification during this Jurassic through Cretaceous interval. And of these new families that are originating during this time, the vast majority of them are parasitoids. These are insects that target other insects, and they particularly target the Coleoptera, or beetles, and the Diptera, or flies. And so it appears that what's happening here is that we have an evolutionary arms race between the tiny parasitic wasps that attack insects and the insects that they attack. And these tiny parasitic wasps are really very specialized, at least at the level of family, in terms of the insects that they are targeting. And so we have this positive feedback loop of diversification of insects that is caused by these parasitoids. And so if you want to read more about this, then please check out the recent paper that I published with my co-authors in the journal Proceedings B. And with that, I would like to acknowledge my co-authors, the Paleobiology database, which was my source of data, as well as my funding source.